Okay, we're at section 14.5, fluid dynamics. Everything we've discussed so far has been just water or a fluid in just static conditions. Now, fluid dynamics indicates that it's moving. And these are two examples here. This car in a wind tunnel, test wind tunnel, is showing the laminar flow of the airstreams above it, and you can see each of these lines is uh, there's no turbulence from these lines. As you look in the next photo, you can see at the bottom near the ashtray you have laminar flow. There's no turbulence, but after what looks like about um, you know 10 centimeters or so, you get this turbulence. You get this uh, haphazard flow. So the laminar flow, each particle of the fluid flows in a smooth path, and the turbulent flow, irregular, unpredictable flow, is characterized by small whirlpool-like regions. So uh, ideal flow, we're going to discuss ideal fluid flow, and there's four conditions that we need to consider. The fluid is non-viscous. The In other words, the viscosity, I think you understand what viscosity is. You think of oil, or you think of molasses. Molasses is very viscous. Water has very low viscosity. The flow is laminar. In other words, there's no turbulence in the flow. There's no eddies. There's no angular momentum. The flow is just laminar. The fluid is incompressible. The If it goes through a constriction, we'll learn that the velocity has to pick up. The water doesn't compress, and the flow is irrotational. Again, there is no angular momentum. So these are the idealizations that we use in um, fluid dynamics. So when we have these conditions, the fluid flows in streamlines. At each point along its path, the particle's velocity is tangent to the streamline. You can see the little red velocity vector is tangent to the one of the lines that is indicated. Okay, so let's look at the continuity equation for fluids. We look at this pipe that has a fluid in it. The pressure at point one is P1, um, and there's an area one, and there's a velocity. There's a velocity to it, and you will get that velocity by this delta x1 times the time that it takes to get through there. And we'll see that this volume here is the same as this volume here. The pressure at point two is P2, and there's a velocity there, and there's uh, uh, the the pressure here, P2A2. It's negative because it's in the opposite direction of the initial. Um, so the mass one is equal to the density times the area times delta x1. Well, what is delta x1? It's determined by the velocity times the time. Uh, so delta x1 is equal to v1 times delta t. M2, this area over here, is equal to the density. The density is the same. Remember, there's no compressibility. The density times area 2 times x2, which is equal to the density times area 2 times the velocity 2 times delta t. Well, M1 equals M2, or so delta, um, I mean, uh, rho alpha 1 V1 delta T equals rho A2 V2 delta T. Well, the rho is the same, the delta T is the same. So we come up with the continuity equation, A1 V1 equals A2 V2. And that's a constant. And you can see that if you're out watering your grass and you just hold your hose with no constriction, the water will let's say it travels a meter. Well, if you put your thumb over the nozzle and to constrict the opening, it'll shoot out further. You uh, constricted uh, the the area. So if the area decreases, the volume has to increase. A1 V1 equals A2 V2. That's a constant. So if the area decreases, the volume has to increase. Um, so and they show it there. Uh, you put your thumb over a hose and it increases. Okay, and that's it for fluid dynamics. We're going to go on with Bernoulli's equation in the next section.